In this session, we're going to talk about the transition from using truth tables to analyze arguments for validity to using proofs. This material comes primarily from Chapter 6 and Chapter 7 in your textbook. Chapter 6 focused on truth tables almost exclusively. We'll pick up with just one of the tail issues there as we make the transition into a discussion of proof in Chapter 7. Now, when it comes to analyzing arguments using truth tables, you know already that that can get very complicated very fast. Here's an example of an argument that we could use a truth table to analyze. You have 1, 2, 3, 4 premises and a conclusion, and you have 1, 2, 3, 4 statement letters, which means that the truth table that you would write to analyze this argument would be 16 lines long. The idea behind using a more simple or simplified method like an abbreviated truth table is meant to short-circuit some of that work. It's meant to provide us with a means of getting to the answer to the question, is this valid, without having to look at all of those lines. Now, the way you would do that with a truth table is you would set up on the left all of the letters and then write out the truth values and then work your way from left to right. Here, what we're going to do with this abbreviated truth table is we're going to find or try and find that one line on which the premises can be true and the conclusion can be false. Now, the way we can do that is we can assume that our conclusion, in this case J, is actually false. And then what we do is we see if we can find an assignment of truth values for the other statement letters that make the premises true. Okay, so if we can do that, if we can assign values, T and F, to all of these statement letters and get all of these true and the conclusion is false, you know the argument is invalid. You have found that one line on that truth table without going through that 16-line process. So let's see if we can do that. Now, I've put numbers up on top here to indicate the order of the steps that I would go through in this process. The first one is you assume that the conclusion is false. Then, of course, that has some implications for the truth values over here. If J itself is false, then the negation of J would have to be true, right? Well, the objective here is to make these premises true if we can. And notice that we now have the true antecedent of a conditional statement, right? That forces us to fix the value of G as true also. Because if G had a value of F, then you'd have a conditional statement with a true antecedent and a false consequent. That would be false. Okay, so this is our third step. We know that if J is false, the negation of J would have to be true. Then G would have to be true in order to make this premise true. All right, well, G occurs in other locations as well. So if G is true here, obviously it's true over here. Now we have another conditional statement where the antecedent is true and the consequent, in order for this whole thing to be true, must be true as well, right? All right, so that's our fourth and fifth step. And so far what we've done is we've made this premise true and this premise true, and the conclusion is false. Okay, but establishing a value of true for H carries over to this conditional statement. We have a true antecedent, so we would have to have a true consequent in order to make this premise true. But notice we now have a conflict between this claim that I is true and the truth value of this premise, which now must be false, because if I is true, its negation must be false. So the lesson here is that if we assume our conclusion is false, we run into the problem, if we're trying to make all our premises true, that that I has to be true and it has to be false at the same time. That cannot work. So what this shows is there's no case in which we can make the conclusion false and all the premises true. The lesson here is that this is a valid argument. Now, this simplifies this whole process of analyzing arguments for validity. But as arguments get more complex still, this method becomes cumbersome. In fact, we can use the insights of Chapter 6 to develop a system of deduction that makes our lives much easier. All right, and what we're going to do now is talk about the concept of an inference rule, and I'm going to explain that concept and then give you a couple of examples of proofs. Okay, now in your textbook, in the back cover, you have a list of rules that are called inference rules, and you have a list of rules called rules of replacement. The basic idea behind these rules is fairly simple. If we go back to what we did in Chapter 6, and we think about something like modus ponens, okay, modus ponens is an inference pattern that looks like this. You have a conditional statement, if P then Q, P therefore Q. Now if you do a truth table for this, you'll see that there is no line on which the premises can be true and the conclusion is false. Right? Now the idea behind an inference rule is this. You're taking an insight like this and you're generalizing it. Now you'll notice that when you move into Chapter 7 of your text, the symbolism from Chapter 6 changes a little bit. When they talk about inference rules, they talk about lowercase P's and Q's rather than uppercase P's and Q's. Let me see if I can find a pen that works a little better here. Here we go. Okay, lowercase if P then Q, P therefore Q. This is the symbolism that's used to talk about the inference rules. Now, what's going on in that shift is this. When we recognize that a conditional statement and its antecedent are affirmed, and we know that the consequent must follow, that holds generally. It doesn't matter what we put in for the antecedent and the consequent. If you have something of this form, if the premises are true, the conclusion must be true also. So I'm going to shift over to the board to my left to give you an illustration of this. If we had something of the following form, P and R or not S, and we put that in brackets, so make sure that we see it as one piece, then T and not V. Okay, let's suppose this is a premise, premise 1. And our second premise is P and R, or not S. Then the idea behind the rule of inference is this. We have a conditional statement, if P then Q. This part is the lowercase p. This part is the lowercase q. And here we have the antecedent, P, right? We have something of that form. What we're guaranteed, given the nature of logic, is that the consequent, T and not V, follow from these two claims. Now, it becomes very cumbersome to analyze arguments and truth tables that have lots of sentence letters. So the shift from Chapter 6 to Chapter 7 really is about shifting from the truth table method to a method that uses these general rules where we're guaranteed if you have these claims and you know they're true, some further claim is true also. So if you think back to your high school geometry class where you were given proofs, you're given some information in the beginning and you're told that you have to prove a theorem of some sort. You go through these steps. You apply the rules of good reasoning, good geometrical reasoning, to the information that you're given in the problem, and you work step by step down to the theorem that you're trying to prove. And what you know is that if the information in the problem is true, and you've followed those steps appropriately, boom, you've reached the theorem, and you know that must be true also. It's precisely the same thing in logic. What we do is we take this system of rules called inference rules, which are basically generalizations of those inference patterns we analyzed in Chapter 6. And we apply those, instead of on the truth table, to the concept of proof. Okay, let me talk about proof for just a second. A proof is simply a step-by-step process where we work from given information by a system of rules down to a conclusion. Now, any valid argument will have this property. You can take the rules of inference and the rules of replacement that we'll talk about in a moment, and if you apply them correctly, you can get through this system of steps from the premises to the conclusion. the conclusion follows according to this system of rules. Okay? Now, the reason the rules are introduced as they are, there are various systems, and we could have come up with a slightly different set of rules, but these rules correspond to the inference patterns like modus ponens and modus tollens that we've analyzed in Chapter 6. All right? Now, I think there's nothing better than seeing an example of how these rules are applied to bring this idea home of a proof. So what I'm going to do is clean up this mess right here, and then I'm going to give two examples that will be helpful. Okay, we're ready to move on to an example in just a second. Before I do that, I want to make sure that we cover both an instance of the rules of replacement that you see in your textbook and the rules of implication. Now, I've already in the last session explained what the rules of implication are about. You know, for example, that modus ponens that you've analyzed in the truth tables is generalizable, and anything that has this form, complex antecedent, complex consequent, the affirmation of the antecedent, then the consequent. You know that truth carries over from these two claims to this claim. So this is a rule of inference. This is a valid argument form, and we turn that into a rule. Now, the rules of replacement are really rules of substitution. If you see something of this form in an argument, the rule of replacement we call De Morgan's rule allows you to replace this with this. Why is that the case? Because they are logically equivalent. That's what these four dots means. They're the same thing, essentially. Now, how do we know that? If you're feeling comfortable with truth tables, I would recommend you run a truth table that compares this statement with this statement in two columns, right? Set out the P's and the Q's, and then run the truth values for both of those claims. And what you'll see is, on every line, this has the same truth value as this, and vice versa, obviously. The same is true for these lower two. Okay, if you have the negation of P or Q, that's the same thing as saying not P and not Q. Intuitively, this should make some sense as well. You don't have to run the truth table on this. You know that a statement which is a disjunction, P or Q, you know that that is false exactly when P is false and Q is false, right? That's essentially what this affirms here. So these statements are equal in terms of how they behave in a truth table, in terms of the truths and the false that we use to analyze them. Okay, that's what allows us to plug in one expression for another in a proof. All right? So that's the motivation behind the rules of replacement, and I've given some motivation for the rules of inference. Now what we want to do is I shift over to this board. So I want to show you how these are applied in the concept of a proof. All right, now here we have an argument that has two premises. It has a conjunction, G and H, or M and G. All right, the second claim is a conditional statement. If G, then T and A. Now we want to prove that A follows from this. You could run a truth table on this, but we can also run a proof. If you refer, as you go through this, to the rules of inference in your textbook, then it'll be easier to follow along. But let's see how we can do this. All right. We want to go through a process, a step-by-step process, where we're applying either a rule of inference or a rule of replacement to this information. And we're trying to get down to a line where we just have A by itself. All right. Well, what we can do from the first premise is rewrite this as G and H, or G and M. All we've done is shifted the order of that conjunction, and the rule for that is simplified as COM, which stands for commutativity. Okay? Now, the reason we want to do that is because now we can apply another rule to this line. Okay, a rule called distribution, right, which says, well, actually, it's a rule of replacement. Okay, the rule of replacement says that we can rewrite 3 as G and H or M. Okay, the reason is this line is logically equivalent to this line. If we ran a truth table and analyzed both of those in columns next to each other, we'd see that they have exactly the same truth value. Now, this comes from the third line, and the rule that we reference is distribution. And I should have put here that this comes from line 1. You always want to put the line that you're applying the rule to, the rule of replacement or the inference rule, and then cite the rule or cite the rule that you're using. All right, so we've taken premise 1, and we have rewritten it here using one rule, and rewritten it again using a second rule. Now, what you don't want to do in this kind of proof is just jump from here to here. Okay, part of the rules of the game that we're playing is that you have to apply these rules individually, one at a time. So it may seem cumbersome, but it gets us to think about the proof of this argument in a step-by-step format. Okay, so don't skip steps. That's the point here. All right, now we have G and H or M. We can apply an additional rule to called simplification to get G out by itself. If we have a if we have a conjunction, G and H or M, we know this is true when G is true and H or M together is true. Any conjunction, if true, requires that both its parts are true. That means if this line's true, we're guaranteed that this line is true also. All right, so this follows from line 4 by the rule of simplification. All right, well, you can see where we're going with this, I hope, because now we have G by itself. We see that in the second premise, G is the antecedent of this conditional. All right, so now we have a conditional statement, G then T and A, and we have the affirmation of its antecedent. That is, the antecedent of that conditional is taken to be true. Well, what that means from modus ponens is that T and A must be true also. So from lines 2 and 5, and the rule we call modus ponens, we can get T and A all by itself. Now, the rule of simplification, as it's written in your textbook, only allows you to pull the leftmost piece of a conjunction out. We can't use simplification here to pull out A because the rule says only the leftmost component. So the seventh line here will simply be a rewriting of line 6, A and T. Okay? And that rule comes from line 6, and it's the same rule that we used up here, commutativity. So we cite COM as the rule. And now we can simplify out for A. So the 8th line would be A all by itself. And that comes from line 7 and simplification. Okay, so in 8 lines, what we've done is we've taken 2 premises that were part of the original argument, and we've either replaced them with things that are logically equivalent or used rules of inference to pull pieces out and in the interest of getting the conclusion by itself. Now, because of this fact, each of the rules of inference preserves truth. If you apply them, you know what you get is true if the premises are true. And because the rules of replacement only substitute equivalent pieces of information into an expression, we're guaranteed if these are true and these rules have been applied correctly, this is true, 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 and ultimately our conclusion must be true also. That's what proof is all about. And this, once we develop some facility with using the rules, is actually much easier than doing a truth table for these kinds of things. Okay? So, that's an example of a proof. If the argument were invalid, of course, you could not get to the conclusion. Okay? So the proofs that we are going to run are only on valid arguments because only valid arguments have the connection between the premises and the conclusion in this way. All right? Now, I'm going to talk about 2 additional kinds of proof that come up late in Chapter 7. The conditional proof and the indirect proof. Typically, people have trouble with both these proofs. So I'm going to give a brief account of what these proof types are, and then I'm going to give an example of each. There are 2 proof types that are sometimes difficult for students to get their head around, at least at first. One is the conditional proof. And I have a problem here that's a conditional proof problem. And the other is something called indirect proof. Now, I'll go through both of these. I'll do an example of each and give a little explanation first. The idea behind a conditional proof is this. A conditional proof takes place when you are trying to establish a conclusion that is a conditional. A conditional says that if one thing is the case, then something else follows. You're not saying that A is the case in this condition. You're saying if it's the case, then it has this particular relationship to K. Right? So I could say if the moon is made of green cheese, then one could eat it. Clearly the moon is not made of green cheese, but if it were, then one could eat it. Right? The idea here is that you're trying to establish a relationship between two claims. Now, how do you do that? How do you do that? Well, the idea is that you want to assume, for the sake of the proof, that the antecedent is true, and then see if you can get down to the consequent through this process of proof. It's a little like arguing in the following fashion. If you say to me, if it rains, then the game will be canceled, and I ask you to prove it, you might reason in the following way. Well, let's suppose that it rains today. It's an open field, and so the sod is going to get saturated, and the coach wants to make sure that the players are safe, they're not susceptible to injury on the wet surface and so on. So the coaches are going to cancel the game. So if it rains, then the game will be canceled. What you've done in that form of reasoning is you've made an assumption about the antecedent being true and reasoned down to the consequent. And then you've shown, well, if that, then this. That's the idea, the intuitive idea behind a conditional proof. And so you have a rule or an approach, a strategy of sorts, that allows you to apply that intuitive technique in a more formal way in this kind of example. So let's take a look at this particular example. These are the premises, 1, 2, and 3. Here's the conclusion that you want to establish. If A, then K. So the approach of a conditional proof is this. This is going to be a little awkward, I think, with my table here. You're going to assume A is the case. All right? And you're going to cite this by the reference ACP, which stands for Assumption Conditional Proof. Once you've assumed that, then you're going to use this assumption plus the information in your premises to see if you can get down to this claim, K. And if you can, then you've proved what you need to prove. All right. So notice here on line 3 we have a premise where, because it's a conjunction, we can simplify out B, right? It's a conjunction. It's true if both its conjuncts are true. That means if this is true, this must be true also. Right? So this comes from line 3 and the rule simplification. All right, now keep in mind where you're going, where you're trying to get to when you do a proof like this. What's the point of getting B by itself? Well, you see that B appears in both these premises further up, which are conditionals. And so you want to see if you can get the antecedent so you can pull out the information in the consequent. Now, we can do that using an interesting rule called addition. If you have a claim like B all by itself, then if that's true, you know that B or F is true. Why? Well, because a disjunction is true if one, the other, or both its parts are true. So if B is true, you know this would have to be true because you're guaranteed that this part of that disjunction is now true. Right? So 6 comes from 5 and this rule for addition. Right? We've added a part to that. And that gives us the antecedent of the conditional that appears up here in our first premise. And that's useful. Now we can apply modus ponens to pull this out. All right? So we get next on line 7 the consequent, A, then G. Okay, this comes from line 1 and line 6 and the rule modus ponens. All right, so that's useful because we have, in addition to if A then G, A up here on line 4, which is going to allow us to pull out G. All right, and that's what we're going to do. On line 8, we get G all by itself, and this follows from lines 4 and line 7 by modus ponens. Okay, now this is going to prove useful because we see that G is part of a conditional here, and don't forget we're trying to get K. So if we can get B or E, then we can get this conditional out on a line by itself. Then we can use G to get K on a line by itself. And that's the strategy we're going to take from here. On line 9, can you see this okay? Line 9, we're going to have B or E. And that's going to come from line 5 and this rule addition that we've applied already once. Okay, now what we're doing here is we're adding E so we can use this premise to get this conditional. So on our 10th line, and then I'm going to shift over to the other side of this board here so you can see a little more easily. On this 10th line, we get if G, then K. All right, let's see. I have another pen here. It works a little better. Fortunately, I do. Okay, so we have if G, then K, and this follows from 2 and 9 by modus ponens. All right? Now, we have G. We have if G, then K. That gives us, let's shift over here to line 11. That gives us K by itself. That comes from line 8 and line 10 by another application of modus ponens. Okay, so here are the premises of our argument. We're interested in whether or not we can establish this conditional claim. We make the assumption that A is true, and then see if we can derive K from all of that. Now, this process has led us to the point where we do have line K all by itself. And what we then do to conclude this proof is show that, well, if A is true, then K is true, and that follows from lines 4 through 11 by the rule CP, which stands for conditional proof. Okay? That's the approach that we take. There's a good example of how you apply this particular strategy to derive a conclusion. That said, I'm going to shift over to the other board so that I can talk about indirect proof. Now, indirect proof is a strategy for proving a conclusion that begins with the assumption that the conclusion is false. Now, this shouldn't be too strange because the beginning of the last session I talked about indirect truth tables. And what we did there was we assumed that the conclusion was false and then tried to show that a contradiction arises when you try and make the premises true. If that contradiction arises, then you know that the argument is valid because you cannot have a false conclusion and true premises. Similarly here, you're given these premises and you want to prove that the conclusion is true. Well, if you assume that it's false, which is the same, in effect, of assuming that R is the case, right? If you assume that R is the case and you're trying to prove not R, and you can argue your way down to a contradiction, something of the form P and not P, then in effect what you're saying is, well, if these are true and my conclusion is false, I'm going to get a contradiction. That means my conclusion cannot be false. It must be true. All right, so it's called indirect proof because you're assuming the opposite of your conclusion. You're trying to derive a contradiction. And then just as the case of the indirect truth tables, that shows you that your conclusion must follow from the premises. Okay? So let's work through this example. I'm making the assumption here that R is the case, and the assumption is referenced as assumption for indirect proof, AIP. That's how you'll cite this. And then you simply use this information in connection with the premises to work down to a contradiction. Okay, so we have R. Now notice we have R, and here we have R or S. So one useful approach might be to use the rule of addition to get R or S. This comes from 3 by ADD, addition. Okay, not attention deficit disorder, although at this point in the proof you may be feeling a little distracted. Okay, line 5. Well, what do? We have R or S, which is the antecedent of this conditional. That allows us to derive H and not G. Okay, that comes from 1 and 4 and modus ponens. Is this showing up clearly on the... Okay. All right, I'm going to have to write a little smaller because there are a number of lines in this particular proof. Okay, so we also have K or R here. Now we have R here. What we can do is get R or K from line 3 and addition. But what we would have to do in order to use this piece of information to get this consequent is we'd have to switch the order of these two, right? So from R or K, we rewrite this as K or R, and that's from line 6, and the rule we refer to as COM, okay, commutativity, K or R. Now once we have K or R, we can then derive G or not H. So on line 8, using this piece of information and this conditional, we get G or not H. That comes from lines 2, 7, and modus ponens. Okay, so what do we do with this? G or not H? We are going to actually use this line, line 5, which has H and not G, to simplify and get H by itself. And you'll see how I'm going to use this with line 8 to get out G on its own. And then we're going to get out not G on its own, and there's your contradiction in the making. Okay, so we get out H from line 5 by the rule of simplification. Okay, that's a conjunction. And then on line 10, we can rewrite H as not H. Right? That's the rule of double negation. Okay, and now you can start to see how this piece of information will work with that piece of information. If we get not H, and then on line 11, and I'm hoping that this is clear, on line 11 we can rewrite line 8 to get not H or G. That's from 8 by commutativity. And the reason we want to do that is now we can use line 10 and line 11 in something called the disjunctive syllogism to get G by itself. We have not H or G. It's not the case that not H. Well then, on line 12, it must be the case that G. So we get from 10 and 11. And let me cite this properly. Double negation. Disjunctive syllogism, DS. We get G by itself. Now I'm going to shift over here to the following line so it's a little easier to write and a little easier to see. Okay, so we have G. Then line 13, what can we do with G? Well, if we look back up here, we have on line 5 H and not G. The rule of simplification, as I've said before, only allows us to pull out the leftmost symbol. But we can rewrite 5 as not G and H by the rule we call commutativity. Okay, and then on line 14, we can pull out not G from line 13 and the rule of simplification. Okay, Now, looking at all of this, what do we have? We have line 14 that says it has the negation of G. On line 12, we have G by itself. That means that we have G and not G. Okay, and this rule is called conjunction. If you have two parts on separate lines, they're both true, then you know the conjunction that puts them together must be true also. So this comes from line 12 and line 14 and the rule we call conjunction. All right, so let's regroup here. We wanted to prove the negation of R. We assumed for the indirect proof that the opposite of this was the case. And now we have used that assumption plus the premises to derive a contradiction. The lesson of this is that not R must be the case. If we assume R and we get a contradiction, then the opposite of R must be the case. That is not R, which happens to be our conclusion. That's where we wanted to go. All right, now the way we cite this is we cite the lines 3 through 15 and the rule, or the citation, IP for indirect proof. And we make a note in our proof. We draw a line alongside all of the information that followed from our assumption right up to the end there. Okay? So we've proved not R using this indirect proof method, and this is a good example of how you would go step by step through this process. Trust me, it is easier than using a truth table.